section is a section that will eventually repeat in pre-calc. So it's a good one that to get as much out of it as you can, because you're going to see it again next semester for those that are going to take it. Now, we just finished doing all the set theory stuff. Today we're going to, this has a little bit to tie into it, but we're going to do a little less on the equation part of it, and we're just going to actually do a lot of writing out of all our ways in which things can happen. But the fundamental accounting principle says the following: if one task can be performed in A ways and another task can be performed in B ways, then both tasks can be performed in A times B ways. If a series of tasks can be performed in A ways and B ways and C ways and so on, then all these tasks can be performed in A, B, C ways. For an OR situation, the fundamental accounting principle does not apply. If the tasks are mutually exclusive, they involve disjoint sets, A and B, in which the number of A union B is equal to the number of A and the number of B, but there's no intersection of it because they're disjoint. If the tasks are not mutually exclusive, they involve non-disjoint sets, C and D. C union D is equal to the number of C plus number of D minus the number of C and D, the principle of inclusion and exclusion. So, okay, so let's make sense of that. When we talk about two events being mutually exclusive, that means neither one has an effect on the other. So flipping a coin and drawing a card, neither one of those has an effect on the other. There are no sets or no part elements that are the same between them. You can't flip a head of a card, okay? So what that means is that the two sets are disjoint of each other. So they're called mutually exclusive from each other. And if they're mutually exclusive, it doesn't have anything to do with each other. However, something that is not mutually exclusive is if you have a bag of marbles, 6 red, 4 orange, and you pick out one marble, and then you got to pick out a second marble, then those events are not mutually exclusive, meaning it depends on what you pick on the first marble as to what you're going to get on the second. Okay? So unless you replace it, and if you replace it, then it doesn't matter. All right? So what we're going to do is we're leading up into probability. But in order to do probability, we have to learn the accounting principles first. So the easiest way for me to explain it is to show you examples of it and then explain what happens here. So Kim is choosing a new cell phone. She can choose the 300, the 400, or the 500 model in green, pink, indigo orange, or taupe trim. Kim is deciding whether or not to get a data plan for her phone. How many different choices does Kim have altogether, accounting for the model, the color, and the data plan, or not? Okay, so here's lesson number 1 that's most important to you. When you have to make a decision, you put a blank for that decision that's going to be made. So in this case, how many decisions do I need to make?
You need to make 3.
Make 3 decisions. So I put 3 blanks. In blank number 1, how many choices do I have on the decision? So I'm talking about the model choice, right? How many choices do I have? There's 3 in there. In blank number 2, for colors, how many colors are there? 5 colors. And then how many choices do I have on the data plan?
2.
Yeah, I either take it or I don't. So what the fundamental accounting principle said to you in the last bit is when I have A number of ways, B number of ways, and C number of ways, I multiply them to find out the number of ways in which I can choose these things. So total, there is 30 ways in which I can pick a model number, a color, and whether or not it has a data plan. Now, the best way to solve this question is just to draw your blanks. However, there is an alternative way, and when we come to probability, we use it often as a tree diagram, or something similar to a tree diagram. So, your tree diagram would start like this. Okay? I put the outcome at the end of it. So 300, 400, 500. So there's 3 ways in which I can select that, right? And then each one of these has 5 colors. Give me the list of colors, please.
Green, pink, indigo, orange, and
Whatever taupe is. Okay, so green, pink, indigo, orange, and taupe. All right. Some female obviously did this. Map is blue, red, black, green. Okay. So at the end of these guys, what's my next decisions that need to be made?
data plan.
Data plan. So plan, no plan. This is an example of a tree diagram. And then at the end of this, I could count them. And if I counted all of them, all of these branches right here on the ends, I'd have 30 different ways in which that would happen. Go ahead, Dylan.
Yeah, but for the 500 model, there's only 3.
We're not there yet, man.
Okay.
Well, that's the next question. So when I counted all these branches, there would be 30 because there's 5 here, 5 here, and 5 here, which makes 15, and each of those 15 has 2 off of it. So it makes 30. So I'm not drawing it all out. It's drawn out in your book if you need to look. Okay, so that's the first one. So the first thing that you want to remember is each decision gets its own blank, and the number of choices in that blank tells you helps you find out how many ways you're going to have. Number of ways in which that's going to happen. Okay? So let's look at the second part of this question. The store agent advises Kim not to choose the 300 model if she wants a data plan. Also, the 500 model is not available in indigo or taupe. So how many choices does Kim have now? Okay. So this one isn't as easy with the decisions, although we could do it with cases. Okay, we could do it with cases in order to find out. So for example, I'm going to show you this. I'm not sure how well it's going to work out. I think it should work out. But here's the thing. So she wants to have the data plan, right? She advises her not to choose the 300 model if she wants a data plan. So she wants a data plan, okay? She's not going to choose the 300, so she's going to choose the 400 or the 500. So what I'm going to do is I'm going to specify. So I'm specifying that if she chooses the 400, then I can find out how many choices she has. Okay? So what I do is I put what we call restrictions in the blanks first. I do my restrictions first. So if I choose this, okay, that means that she wants a data plan. All right, if she only chooses the 400 or the 500, she wants a data plan. Okay? So she doesn't have a choice as to data plan or no data plan. It's got to be a data plan because that's why she chose the 400 or 500 if she wants it. Okay? So how many choices of colors does she have for the 400 model? 5. And how many choices of colors does she have for the 500 model? 3, correct? Okay? So then that would make a total of 8 ways she could choose that if she wants the data plan. Fair enough? Okay? So then you have to go to the 300 and then we have to look into the no data plan. So this becomes inherently more difficult because I got to keep breaking these things down into cases. So as opposed to doing this question with the blanks, all right, because I'm going to miss something, they suggest you do the tree diagram. So if you do the tree diagram, the 300 means that you have 5 colors, right? What are they again? Green, pink, indigo, orange, and taupe. Okay? But if she does that, it's no plan, right? So she has 5 choices there, correct?
Yeah.
And then if she chooses the 400, still the same colors, right? But now she has a choice, right, of data plan, no plan, all the way. Okay, so how many is she gonna have here? How many choices does she have here? 10 choices there, because she can choose the plan or not choose the plan. Okay, and then the 500 has only 3 colors, right? And then each one has a data plan, no plan. So how many does she have here then? 6 choices there. So how many does she have? How many choices does she have total then? 21. So this question here is easier to do with the tree diagram, because you can see all the possible outcomes. All right, whereas the other one, we have too many restrictions to do on it, we have to make our choices. So we're making some assumptions there. So if we actually went back to here, in theory, these would be 2 each. Oops. This. So this is data plan. Whoops, messing this up. That's 2 choices. So this is 10 and 6, right? So it's 16 choices. Okay, because you have a choice of a data plan or no data plan, if you choose the 400 or the 500. But if you choose the 300 model, there's only 5 choices for it, because you don't have a plan for it. So add them all up, and what do I get?
21.
21. So it can be done that way. It can be done that way. But that's the way it looks right now. All right. Let's look at example 2. Example 2 is similar to one we looked at last week. From a standard deck of cards, how many possibilities are there for drawing a 2 or a face card? How many 2s are in a deck of cards?
4.
How many face cards are in a deck of cards?
12.
12. So how many possibilities do you have? 16. Is there any overlap? They have disjoint sets, right? There's no 2 face cards. Face card is number 2. How about a spade or a queen? How many spades are in the deck?
Almost 16.
How many spades? 13 spades. 4 suits, 52 cards. Each suit has the same amount. 13 spades. How many queens are in the deck?
4.
4. Is there anything?
One queen.
1 queen of spades. So then how many possibilities are there? 16. Because you have 13 and 4 and you subtract 1, right? So, here's what I have. Number of spades, union, queens. Right? Number of spades plus number of queens minus the queen of spades. $13 plus 4 minus 1. 16 cards. Good so far? All right. Let's look at 4.2. First couple sections here are going to go quick, and then after that it gets to be a little bit tougher for you. All right. number of permutations or ordered arrangements of set n different objects is given by the expression n factorial. Whereas n factorial is n times n minus 1 times n minus 2 times all the way down to, it's called factorial. Okay, what does that mean? Easiest way to explain that is this. Okay, first of all, the exclamation mark is a math term referred to as factorial. And what it implies is that whatever that number is, you multiply it by every number after that until you get to 1. Four factorial. Times 1 less than that, times 2 less than that, times 3 less than that until you get to 1. That's what that means. 4 factorial means 4 times 3 times 2 times 1. Okay, so far? That's a new notation for you. All right? So to write that in terms of n factorial, the first number is n. The second number is 1 less than n. How do I show that? And then 2 less than n. Yeah. And then n take away 3 all the way down to 1. Okay? That's what n factorial is. Take out your calculators for a second, please. If you have super duper large numbers, there is a function on your calculator that you can find. So everybody put in 6. Put in 6. Go to math. Go all the way across the probability, that's right. And the fourth one down is exclamation mark. So hit enter and enter again. So 6 times 5 times 4 times 3 times 2 times 1 is 720. Okay? So that's on there. We need to know that, where that is. So let's look at the first thing on 94 here, the first example. A 6-digit secret code number uses the digits from 1 through 6 exactly once each. If the first digit of the code is a 3, and the last digit of the code is 2, how many possibilities are there for this code number? Okay, first things first. Without any restrictions on it, how many possibilities are there for a 6-digit code in which you only use the numbers once?
36.
How many decisions do I have to make? 6. Make 6? 1, 2, 3, 4, 5, and 6. How many choices of those 6-digit numbers do I have for the first one?
6.
The second?
5. Oh, so it's 720.
Which is equal to 720. So if I have no restrictions, other than I can only use the digits once, for a 6-digit code, there's 720 ways I can put that code in. All right? But it says what? First number has to be 3. And the last number has to be 2. Okay? So here's the thing. I showed you this a little bit earlier and I didn't explain it very well, so I'm going to explain it well now. When you have a restriction and you're putting something specific into the blank, these questions will ask you to always give an explanation. Well, the explanation for you just comes to whatever's in the squiggly brackets below. So in this case, the first number had to be a 3. So there's only one decision to make. It has to be a 3. The last blank has to be a 2. So there's only one decision to make there. That number has to be a 2, so it can't be anything else. So now, how many choices do I have for that blank? 4. 4? This one? 3. So if I want a 6-digit code that starts with 3, ends with 2, how many possibilities can I have?
24.
24. 4 factorial. 24 possibilities. If I have that restriction on it. Okay, here's a question for you now. If that 6-digit code needs to be even, how many possibilities do I have?
What do you mean needs to be even, like all the numbers need to be even?
No. How do I make an even number? The last digit has to be even, right? So I want a 6-digit code in which that last number is even.
Without the restrictions on
No, just start the question over again. Okay, do it again. The only restriction on it is that that last number has to be even. Okay? So, it's blanks, right? Last one has to be even. How many choices do I have? 3 choices. So I pick one of those even numbers. How many choices do I have here?
4, 3, 2.
As long as I do my restrictions first, everything else just falls into place. Okay? So 5 factorial times 3, 360, right? Okay? It's just another example. Any questions about that so far? Restrictions got to be done first, and then you do everything else. Right? How about this guy? Simplify. N plus 3 times n plus 2 factorial. What's on the bottom? N plus 1?
Yeah.
N plus 1 factorial. It asks us to simplify that. First question for you is this. Which is the larger number, the numerator or the denominator? The top or the bottom? Which is the larger number? The numerator? How come you think it's the numerator?
Well, you assume so because it's n plus 3 and n plus 2, so there's 2n, and well, if you FOIL it, you just end up with more n's than you do on the bottom.
Okay.
So.
Okay. Rationale's
n is
there.
Positive or negative.
Yeah.
Yes.
Rationale's there. But let's say the number's 4. What does that mean the top number starts with? If your n is 4, what is your top value? What's this value right here? 7. And then 6. And then what's the next one you multiply by? The next one below this, right? Which would be 5, and then 4, and 3, right? Okay. Here's how this looks. If I expand this a little bit, and I always expand the larger of the values. So if I expand this, what's the next number in the sequence? Because of the factorial, what's the next number in the sequence?
N plus 1.
There it is, simplified. N plus 3 times n plus 2. Okay? So you expand the top part. Now, let me show you this using numbers. So it makes more sense. Okay? Let's say the top part was 7 times 6 factorial over 5 factorial. Okay? Because that's essentially what I've just done. Expand the top. 7 times 6. What's the factorial mean? I gotta multiply everything below it, right? So 5, 4, 3, 2, and 1. Do we agree? Is that what 6 factorial is? Yeah? What's 5 factorial? That's what I just did. What was I left with? 7 times 6, n plus 3 times n plus 2. Okay? This isn't very complicated. Let's do the second one on it, just so that you're not. The second one is this exact same thing, Alright? Except now, we have to find out what n actually is. So now we have to find out what n actually is, because this whole thing is equal to 30. So, do exactly what I just did. Right? Cancel, cancel. All right. What does this statement read to you as? In words,
The product of two consecutive numbers.
Yes.
is equal to 30.
yes. What are those two consecutive numbers?
5 and 6.
5 and 6. Awesome. Awesome. That's exactly what that reads. What am I looking for? Two numbers that I multiply, two consecutive numbers that I multiply to give me 30. So 5 and 6 is right. So then what does n have to be?
3.
N has to be 3, correct? I agree with you. But it's not that simple in terms of how do you show the work. Okay? So here's what I'm going to do. I'm going to FOIL this. N squared plus 5n plus 6 equals 30. Okay? Subtract 30. N squared plus 5n minus 24 equals 0. Can I factor this? Are there factors of negative 24 that give you plus 5?
Negative, 8, -3.
Say that again.
8 and negative 3.
8 and negative 3. N and n agreed? Plus 8 minus 3. Therefore, n is equal to negative 8 and 3. I can cross that out because you cannot have a negative factorial, because the factorial only goes to 1. So what is the correct answer for this question?
N is equal to 3.
3. So n is equal to 3. Okay, so a couple things that we have to remember. Number one is you expand the larger number to cross it out with the bottom, with the lower number. Now it could be different on top and bottom. Second thing is, we understood at this point that that answer had to be 3. But you need to show that there is a possible answer that needs to be discarded, what we call an extraneous root. An extraneous root is any answer that we get that cannot work for the question. And you need to cross it out with an X and show that you actually got that as part of your solution. So that would be an extra half mark on your exam to get to that point right there, where you have to cross out the negative 8. Okay? Any questions about that so far? Now you do have your calculators. You can use your factorial button, but for the most part, they want you to figure a lot of this out in your head. So, for example, if I have this, I'll pull the calculator out. What is 6 factorial over 3 factorial? What's it leave me with?
6 times 5 times 4.
Very good. 6 times 5 times 4, which is equal to 120. Okay? Because when you expand it out, 6, 5, 4, 3 factorial, there's 3 factorial on the bottom, those cancel. Okay? There's 4, 1, and 4, 2. So test is tomorrow. We'll go to 4, 3, and 4, 4 on Thursday. All right? Anyone have any questions from your pre-test on Friday?
Yeah, we'll go with those.